Swayam Prabha. Digital India. Educated India.
We are welcoming you back into our lecture series on advanced hydraulics. We are in the third module on varied flows. So, if you recall from the last class, we had discussed on the higher order approximations that can also be used for solving the dynamic equation for gradually varied flow. One such method that we discussed was the fourth order Runge-Kutta method. We also had solved a demonstrative problem for the trapezoidal channel section using this fourth order Runge-Kutta method. So, we had done an extensive demonstration on that problem, and I hope you all have benefited much. You have understood the concept on solving that problem. If you recall the dynamic equation for gradually varied flow, you have seen that the equation, the dynamic equation as given here, it is a function of the spatial variable x and the depth of flow y, isn't it? So, that is dy by dx is function of x and y. This, according to your mathematical principle, you can integrate it in the following form, that is integral dy is equal to integral of f of x y dx, as you are taking a channel reach. Say if you are taking a channel reach between two sections 1 1 and 2 2. If you take two sections like this, here if the depth is y 1, this is depth 2, depth is y 2. Say this is at a location x 1, this is at a location x 2, then the corresponding this integration can be provided in the following form. That can be again rearranged, and the solving is done usually in this particular form. So, the various forms you have seen already, how to evaluate y 2 based on the value given at y 1. So, this is called the step process. You have seen the direct step method, you have also seen the Runge-Kutta method. Today, we will see the standard step method for gradually varied flow computations. So, the standard step method, it is normally used for non-prismatic channels. The standard step procedure is used for non-prismatic channels. See, as given here, if there are two non-prismatic channels in a particular reach, say if this is the reach of the channel you are interested, or you can give it as del x also, it does not matter. And if you want to evaluate the flow properties in this particular non-prismatic channel, you use the standard step method. So, how do you evaluate them? How do you incorporate them? So, you know that say this is channel section 1 1 and this is channel section 2 2. Let us assume that the depth of the flow here as well as the velocity of the flow here, they all depend not only on the depth of flow, the velocity of the flow depends not only on the depth of the flow, it is also the function of x here, right, at which location of x it is. Similarly, here also this is a function of x, the flow properties are function of x, especially the if you evaluate the energy slope or the friction slope, you can see those things. So, they have all the hydraulic properties are, so in non-prismatic channel, hydraulic properties are functions of x and y, both x and y. So, in prismatic channels we have seen that most of the functions are properties of only the depth of flow y, but that is not the case in the non-prismatic channels. So, we have to use these things. So, what they do? Say if you have a reach of channel, a non-prismatic channel, they may conduct various field surveys at various locations. They conduct field surveys, maybe cross-sectional survey as well as longitudinal survey along the reach, as well as the cross-sectional details will be captured at various locations. Say this is section 1 this is section 2 this is section 3 Please note that this is the top view of a channel reach or non-prismatic or a natural channel that is being given here. So, you do cross-sectional surveys, local field surveys are done, you measure the depth here, you measure the depth here, properties there, what are the cross-sectional properties, all those things will be recorded. Once you record all those things, so now you know the distinct site locations of the channel reach. Between between two stations, you can average the properties. So, suppose if all the properties are given here. Now, if you want to evaluate the flow depth at this location and this location like that, you can use the standard step method now. That is also a varied flow property, that is gradually varied flow. Using standard step method, you can evaluate the depth of flow. So, as we mentioned earlier, computations are carried out from a known location. Say at this location, if all the properties are given to you at this location, if all the properties are given to you, then using the step procedure, the step evaluation we have seen earlier in the equation. Say this is the step procedure. The same thing we are using, the same principles we are using here. So, in this thing, at section 2 to evaluate the depth of flow or even the velocity of the flow or even the discharge, as you know, it will be constant, because gradually varied flow we have suggested that discharge is constant throughout all the sections. So, discharge will be same, all these things can be evaluated. So, you use the known property from the left hand side and you evaluate the right hand side. So, how do I proceed now? So, consider the following channel section. Say if I have the following parameters, say if this is your channel depth, say at any depth z from the datum line. Say let me suggest what are these lines. First, let the bottom line be the datum line, and this thick line let me suggest you as the channel bed line, and the next line is the water surface line, and above one is the energy slope line. So, what are these quantities? Datum, channel bed and slope of the channel bed, you know it is given by the quantity S0, water surface line is given like this, and the slope of the water surface is given as SW, if you recall them. Energy slope line, if it can be evaluated, the energy quantities, if it is evaluated, you can easily give this quantity as SE or SF, right? We had given these things. Now, if at a location, if a particular location, if the channel bed of that location is at elevation Z from the datum line, let the depth of flow be Y at that location. And as this is a non-prismatic channel, the cross-sectional details are coming into much prominence here, and not only that, the velocity, if you see that the velocity may not be uniform across the whole cross section. So, you may see you will be taking average velocity, and therefore, you may be incorporating energy correction factors and all. So, the velocity head at this location, it can be given as alpha v squared by 2g. So, if you add all these quantities z plus y plus alpha v squared by 2g, you are going to get the total energy. Total energy H at any section is equal to the datum head called z, small z, plus the elevation of water. Please note that why it is elevation of water. We are dealing with flow in open channels where the pressure is in hydrostatic condition. So, you have to note that we are not dealing with very high speed flows in such situations where you cannot use the hydrostatic assumptions. So, H is equal to z plus y plus alpha v squared by 2g. So, this is the general total energy head equation you have already studied in this case. So, if I consider this as section 1 then the energy head at H 1 is equal to energy at section 1 is equal to H 1 is equal to Z 1 plus Y 1 plus alpha 1 V 1 square. Like this we can write. Similarly, another section 2 if I take, and if that section is at an elevation Z2 from the datum line, the bed of that section is at an elevation Z2, then I can easily write H2 is equal to Z2 Y2, and this is alpha 2 V2 squared by 2g. So, Z2 plus Y2, so I will just give it at as mentioned earlier, H1 is equal to Z1 plus Y1 plus alpha 1 V1 squared by 2g. H2 is equal to Z2 plus Y2 plus alpha 2 V2 squared by 2g. Like this you can give the energy equations for the two sections. So, what do you get if these two sections are separated by a distance del x? If these two sections are separated by a distance del x in the bed, then we can write the following form. I can find, means you can see the water surface elevation from datum. I can just make another parameter now. I can just make another parameter such a way that the water surface elevation, this location at this particular from the datum line, this is now called as capital Z1. Similarly, this elevation, it is called capital Z2. Like this I can just identify two parameters. So, your Z1 is nothing but small z1 plus y1. Similarly, z2 is nothing but small z2 plus y2. From the following figure, can you guess certain quantities? Your z1 is nothing but z2 plus the channel bed slope is given, channel bed slope it is already given to you, that bed slope into this particular distance, that will give you the difference between z1 and z2, right. So, I can write z1 as z2 plus S0 into del x. I can easily write them. Therefore, your capital Z1 is nothing but Z2 plus S0 del x plus Y1. These are nothing but just manipulation or rearranging of the terms. There is no arithmetic things involved here. So, as you see here in this figure, your energy line, your energy, it is getting decreased at section 1 whatever total energy was there H1, it is getting reduced to H2 at section 2. So, what is the energy loss? What could be your energy loss? What could be the energy? H1 minus H2 will give you the energy loss, right? The various energy losses are loss of energy due to friction, that is, you know, friction slope is SF. Based on that, you can evaluate loss of energy due to friction, and loss of energy due to eddy currents. As these are non-prismatic channels, there will be considerable eddy currents also. So, those things also causes loss in energy. So, and a loss of energy due to friction, I can give this particular term as HF and this particular term as HE. HF, the friction loss, it can be given as the friction slope into del x. So, we are going to take the average friction slope. So, between two sections, say in this case, this is section 1 and this is section 2. So, what is the friction slope here? SF1. This is here, it is SF2. Based on these two sections, so SF, you are going to take the average friction slope SF bar, that is given as SF bar is equal to half of SF1 plus SF2. So, you are going to take SF bar and you are going to multiply it with distance del x to give you the loss due to friction. Your eddy loss can be given by HE is equal to some coefficient, that is, say some coefficient KL into the change in velocity. Please note that the change in velocity that is causing them. So, of course, I have to use the energy correction factors also by 2G. So, the eddy loss is given by KL is a energy loss coefficient, eddy energy due to eddy currents and all. So, it is a parameter KL that can be experimentally found out. So, we are not going to going in detail about this particular parameter. So, it can be given by this following relationship, the eddy loss, which is. So, please note that here we are going to take the magnitude in difference between the velocity. So, even as I mentioned, KL alpha 2 V2 squared minus alpha 1 V1 squared by 2G. This is given as a. So, this is the modulus of this difference. So, even if